Hi, this is lesson 7.4, power series, and we want geometric power series, integration, differentiation of those power series. Now a series with variable terms like this, 1 plus, whenever you see this L on my sheets, it's a dot, 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 but 1 plus x squared plus x cubed plus dot, 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 plus x sub n plus dot, dot, dot is called a power series because I have all those powers. And that is also a geometric power series. If it converges, what must be true about the variable x? Well, I put a little refresher up here. When we had the ratio, absolute value of the ratio is less than 1. When that happens, then we do converge. Well, in this case now, I have a equaling 1, and my ratio is going to be my x every time. So what has to happen is that absolute value of x has to be less than 1. What does that mean? Well, that means that x is between -1 and 1. When that happens, this series right here will converge. If it's not like that, then we will not converge. And this is what we'll call our interval of convergence, which we'll talk about a little bit more later, but that is the interval of convergence. And then for these x values, the function f of x is equal to 1 over 1 minus x. Remember up here that a is equal to 1, so that's going to be my a term. And then x is my ratio. So my function here can represent this whole thing here. And that also can be written like this. And this is really, really key. If you can get your head around this idea that these functions can be written as expanded series or as summation notation, if you can get that all together, that's going to help you out a lot. So once again, if we can fight it into these forms, this is an expanded sum. We can write it like that. We can write it with summation notation, and we also can write it as a function. Those three things. So if we work on that, then we should be good to go. So here's some examples. Number 1 says, I give you this power series, or that you understand that this is a power series. Show 4 terms and the general term, and also give the series using sigma notation, and then give the interval of convergence. So now this seems to fit our geometric series pattern, but remember that it's 1 minus x. And so when I look at this, my ratio is actually -x, and my a value is equal to 1. So it says write out the first 4 values. Well, I said my first term is 1, and then my ratio is -x. So I'm going to multiply every time by -x. And so that would be my first 4 terms. If I want to do my general term, I need this alternating in signs. Now look at when it's raised to the 3rd power, I have a negative, so I can go to the nth power, which would give me a negative if it was, for instance, 3rd, and then I can go x sub n. Now I can write it like this, but what happens too is that you got to determine what your n values are going to start with. And so to generate this 1 right here, I need n to be equal to 0 in order to make that work. Then I'm going off to infinity, and then my rule goes out here, and that's what I have. So that's my summation notation. Now my interval of convergence, what we do is we take the ratio and put it in between -1 and 1. So the absolute value of -x is less than 1, which means that the absolute value of x is less than 1, so x has to be, again, between -1 and 1. This is my interval of convergence. If I'm outside this region, then this series will not converge because the values will be too big. All right? So how about number 2? Let's try this one again. Identify R and identify A. Why don't you try that yourself? So if we got r is equal to 2x and a equal to 3, then you're correct. So then we're going to start this off by saying that g of x I didn't do that in the previous example. I should have called this f of x. So g of x also can be written as an infinite series, geometric series, with the first term being 3, and then what do I multiply by? Well, it's 2x. So this is going to be plus 6x, plus, multiplied by 2x again, would be 12x squared. 2x again would be 24x cubed, plus dot, dot, dot. Then what is my general term? Well, my general term is going to be my 3 times my 2x raised to the n power. And that's what we're going to end up with. So I can now write this as an infinite geometric sequence with n equal to 0 to infinity of 3 times 2x, that quantity 2x raised to the n. And that is also another name for g of x. So I have it as an equation, I have it as an expanded sum, and then I have it in summation notation. Now the interval of convergence, what you have to do is take this ratio again and put it less than 1. So 2x is between negative 1 and 1, and so x would have to be between negative 1/2, no, I did that wrong, less than, and 1/2. This is your interval of convergence. If I'm outside of that region, then it will not converge. Now look at number 3. Does it fit this same pattern? Not exactly, but yes it does. If I put in 1 over 1 minus 3x like this, that should satisfy the form that I need for this infinite geometric sequence, or I'm sorry, series. And so it's a little bit of a trick. We put this new chunk in here. So what is that? Well, that tells me that the r is 1 minus 3x, and then my a is 1. So if I want to rewrite h of x in my expanded form, I'm going to have to put in a 1. My ratio is 1 minus 3x. And so I'm just going to be multiplying by 1 minus 3x every time. And then my general term, I'm just going to put it into my rule here. I'm going to start off with n equal to 0 to infinity of 1 minus 3x to the n power. Does that satisfy this one? Yes, if I start at 0, plug it in here for n, that would work. All right, so that would be my sum, or my series, sigma notation, that represents h of x as well. Now the last thing is, what's my interval of convergence? Let me do this in red so you can see it better. 1 minus 3x has to be less than 1, so that has to be between negative 1 and 1. And if I solve that out, then I'm going to add negative 1 to both sides, or every side, so I get negative 2 and 0. Divide by negative. Remember, when you divide by negative, you do the flip. So this is going to be x is greater than 0 and less than 2/3. And we should write it this way. That's convention. So this would be my interval of convergence. That's the values of x where this whole thing will converge to a specific value. Otherwise, it will not. Now this does get a little tricky, so make sure you bring questions, highlight whatever you got to do, bring those to class, and we can talk about them. So make sure you do that. Let's move on to example number 4. Now what they ask you to do is, for example number 4, is using the power series from example number 1, make a new power series for f of x squared. So you're just going to do a composition of function. Wherever you see x, you're going to put in x squared. So we rewrote f of x for you here. If you don't have that down, put that down. And now I'm going to go ahead and put in x squared. So that's going to be equal to 1 over 1 plus x squared is equal to 1 minus x squared plus x to the 4th minus x to the 6th plus dot, dot, dot. And then I'm going to end up with plus negative x squared, parentheses, n plus dot, dot, dot. If I want to put this into a sum as well, we can go n equal to 0 to infinity. This is my rule here now, so this would be negative x to the 2n, negative x to the 2n, and that would also represent this new power series. This is what we're looking at more so because we're going to be integrating and taking the derivative of it later. Number 5, why don't you try this one? Try to make a new power series from what we had in example 2 for g of the square root of x. So pause and try it. So this would be the first step, just put in square root of x. We sometimes call this chunking. Wherever we see the x, we take a new chunk, which is the square root of x, and put it in wherever we see the x. And that is chunking. Now I can simplify this a little bit and go 3 plus 6 square root of x plus, this would be a 4, so that's 12 square root of x squared. And that should be a plain x, right? So I should have just an x here. And then plus 2, that would be 824 x squared root of x plus so on. Okay? So that's what we end up with. And this is the same thing as x to the 3/2 if you wish. There you go. So this is a chunk. Take these chunks and put them in where you see the x. I got to go back to number 4 for a minute. I did this one right here. I did this wrong. This should be n equal to 0 to infinity. I need that negative 1 alternating. And the first term's positive, so I got to go to the n. And then this would be x to the 2n. That would work better. So whenever we see this alternating sequence, we're probably going to need this negative 1 raised to the n power. Now you might want to take a break because we're going to get into this a little bit more extended. But we take these series now, and if I want the derivative of a certain function, I can expand it into its series form and then take the derivative of each piece as we go along. So you decide if you need to take a break right now and come back to this or whatever you want to do. But number 6 asks you to do that. We have the power series from before, right here. And then we have f prime. We want to find f prime. This is f of x in one form and another form. So I don't want to take the derivative in this form. I want to take it in this form here. So f prime of x is going to be equal to, I want that there. I'm going to take the derivative of each piece. What's the derivative of 1? Well, that's going to be 0. Plus 1 plus 2x plus 3x squared. Plus dot dot dot, and then plus n times x to the n minus 1. That would be your general term. Isn't that crazy? We take this function here, instead of doing the derivative of this thing, we're going to take the derivative of this thing, and we end up with this. I think that's crazy. That's fun, huh? I would start graphing some of these sometimes and see how they look alike or not alike. We'll do some of that graphing in class. Now this one already gives you in the expanded form, and then they just want you to find j prime of x. So let's try it. J prime of x is equal to 0 plus 1 plus, okay, so for this term, I got to pull the 2 out in front. 2 factorial is just 2, so that's going to be canceled, so that's just an x. Plus the next one. Take the 3 out in front. That will cancel with one of these, and I'll be left with a 2 in the denominator. So this will be x squared over 2. Plus the next one. That will cancel the 4. So it will be x to the 3rd all over 3 factorial. I'll be left with all the remainders of this just because the 1, 4 will cancel when I pull it out in front. And if we look at this, whoa! This looks very similar to what we just started off with. Isn't that the same thing as what we have up above here? Isn't j and j prime exactly the same? That's interesting, huh? Can we take that information and find out what j of x is? What do you think? Which function is the derivative of itself? Well, some of you have guessed it. That is going to be e to the x. What? e to the x is approximately 1 plus x squared over 2 plus x cubed over 3 factorial plus so on. What? That is crazy. Oh my goodness. We're going to have to see what goes on here. And in fact, if I do this dot, 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 I can make this a solid equal rather than approximately equal. This is called the power series for e to the x, and you'll have to memorize this at some point, and it will come up again. Don't worry, you'll see it. Okay, then power series by integration for number 8. If I give you this fact right here, now look at this is geometric with a negative t, so since I have a negative ratio, this is going to alternate. This is dot, 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 this is dot, 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 and we can write it as I do have over here as well. So now this is the cool thing. I can take the integral of something that's in the function form, and that's going to be equivalent to its form of the integral in the expanded form. So I can do this piece by piece if I wish. So what is the, and here's the deal too, is that you can relate both of these things together and maybe take the antiderivative this side and work it with this side, or vice versa. So I'm going to do both sides here. If I take the antiderivative here, this would be ln of 1 plus t. And I'm going to evaluate that from 0 to x. A lot of times I put a bracket here. You should just put a straight bar, but I don't know why I start doing a bracket. And then this side is just going to be taking the antiderivative, which would be t minus t squared over 2 plus t cubed over 3 minus t to the 4th over 4 plus dot, dot, dot. So we have this whole thing, and we're going to evaluate that from 0 to x as well. So what does that mean for us? Well, this would be ln of 1 plus x minus ln of 1, ln 1, 0, is equal to, this would be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. Uh-oh, we have a new function. ln of this thing is approximately this. That's a power series for ln of x, 1 plus x. Absolute value of that. Oh, wow, is that amazing? Don't forget to plug in your 0, but this is a polynomial, so you get minus 0. Woo! Is that cool? Nice. Now we do have to realize our interval of convergence for this thing. So if we look at this, this is our x between -1 and 1 because I have the negative t value in here, or whatever, x or t, and we take the absolute value of that and it goes away, but I'm going to end up with x between -1 and 1, and that is our interval of convergence. And since that is true, what do I need to do with these absolute value symbols? Well, I don't need them anymore. So ln of 1 plus x is equal to x minus, just all that whole thing, okay? So you can remove the absolute values in that case. Not always, but just check it. Check that interval of convergence. So number 9 then says, I want to take that result that I just got, and I want to write f of x is equal to ln x. So I need to formulate this, and this is kind of that chunking idea. How can I make this thing look like this thing? Well, it's true that ln x is equal to ln. I want to write this as 1 plus some chunk like I have over here. So I'm going to go 1 plus, well, what chunk will work? X. What else do I need? I need to cancel off that 1 so I get this. So this side and this side are equivalent. Does that kind of fit my form up here now? Well, I hope so. And so then I can rewrite this as replacing these chunks now with the x minus 1. So this would be x minus 1 plus x minus 1 squared all over 2. So I'm getting that from there. And then I'm going to go, and that should be a minus. And then I got a plus x minus 1 cubed, then a minus x minus 1 to the fourth, and so on. So that is a way to represent ln x. So this is a power series for ln x. Whoa! We can write it in a different form. That is amazing. That is absolutely amazing. So you're going to be contorting all these functions so that they can mess around and then package together to be one of these different sums, and you're just going to have to get used to it. Get in there and try some things. It'll be fun. So here we go, another contortion. Now write a power series for g of x is equal to x squared times ln x. So here I had ln x, and then I need to just multiply it by x squared. That's a distributive property. So if I have x squared, this is g of x, equals x squared ln x, that's just going to be equal to, take each one of these terms and multiply by x squared. So it's going to be x squared x minus 1, we're contorting, minus x squared x minus 1, quantity squared over 2, plus x squared x minus 1 cubed all over 3, and so on. This is beautiful stuff. Isn't that crazy? I find it amazing we can take this little thing and turn it into this thing here. That is really amazing. Cool stuff. All right, so you're going to be doing a lot of these contortionist movements and taking derivatives and integrals with each one of these parts, and so you got to kind of move them around. There's a lot in this lesson, and we'll just keep on building, but you really got to get into this and really practice this to do well. Thanks for listening, and I hope you have a great day.